Hey, hi guys. I'm gonna try and be tech savvy here for a minute. So, you guys are working on October the 12th. Um, Hopefully your test corrections and things went smoothly yesterday. October 12th. I can't use my tablet here. There we go. I left my good stylus at school. There we go. Okay, so this would be Thursday's lesson. So you guys are now going to start to think about some different transformations from the ones that we did last year. And then tomorrow we're going to talk about putting together what you know from last year with this new little bit of information you're going to gain this year. Um, the other trick this year is we're not just transforming graphs of parabolas, we're going to be transforming graphs of all of those parent functions that we went through last week. Okay, so you can probably see in the background, my video has the rest of my screen. Um, I'm going to go through the bell work, but my suggestion would be that you pause the video, you do the bell work, or that you did the bell work before you started the video, and then just kind of watch me run through it just to make sure that you see that your answers are correct, okay? So I'm just gonna jot down what I need to graph so I don't have to keep flipping because that would be even more annoying than listening to this. Okay, so what we're trying to do today is look at some changes in the horizontal direction. So I'm going to flip screens. I already have our parent function y equals root x there. And then the idea with the bell work was just to see what happens when you change what's happening directly to the variable that's underneath the root. Okay, and hopefully this will help you sort of see how to type things in if you got something wrong. Did I do? Hmm. Mm-hmm. There we go. I don't know, I didn't like the g at x apparently. Okay, so by putting that negative underneath the root, so within the function itself, I know it feels funny because you guys are probably looking at negative root x and thinking I can't take the square root of a negative number. That's true, but this would just mean that all of your values of x would have to be negative, which is shown on this graph here. Okay, so you're okay. But any value you plugged in for x would have to be less than or equal to 0, which is why your graph now looks this way. Okay, so what that negative sign does is create a reflection, but not the way we're used to. We're used to things reflecting and opening down. This is a reflection over the y-axis instead of over the x-axis like you were used to with parabolas. Just going to stick with my f at x here so I don't have another mishap. Now here, when we put a 2 underneath, it's the green graph, so you'll notice, like relative to the parent function, so we always want to look back to that base parent function that we talked about last week. 2 to the x seems to be a little bit above it, I guess, if we're going to talk about the location of points and things. So hopefully you also saw that when you typed it in. And then the next one had like a fraction there, so it was like 0.25 or a quarter of x. And then that one, kind of, these two are a little bit counterintuitive. They're kind of the opposite of what you would expect because we're used to like 2x squared stretching your graph and making it thinner. But when you're working in the horizontal direction, that whole number of 2 or that value that's greater than 1 seem to actually make it, for lack of a better way to describe it, wider. And using the fraction seemed to make it flatter. Okay, and we'll talk about that in the lesson, but that's a key thing for you to note while you're looking at these for the first time. Okay, I'm going to turn off my root functions now and do the next set. So we had 1 over x, so our reciprocal functions, and then we started to mess with that. Transformations of reciprocal functions aren't great, okay, and they're not super fun to do, just because your graph is like increasing so quickly when it gets close to the axis that it's hard to show things like stretches and whatnot, but reflections we can see. So the first one that was here was 1 over, and I'm just going to put in brackets because I want to make the x within the function negative. And you'll notice that it basically reflected. We talked a little bit about symmetry. Remember, this thing had what we called odd symmetry. There's no way that you can tell if the black graph was reflected over the y-axis or the x-axis to produce this. When that will matter is maybe if your graph has moved or something, but there was a reflection of some sort that went on there, and in this case it was over the y-axis, only because I know I typed it in this way and kept the negative in the denominator. Okay, but if the negative were out in front, it would reflect over x and give you the exact same graph. All right, and then we had 1 over 4x. Okay, and that's that blue graph, and you'll just notice that it gets like way tighter to your axes, right? Like this turn here is at a smaller value than here. Like this was at 1, 1, but this point here is now at like a 1/2 and a 1/2. Okay, so you can sort of see the difference with that point specifically, in that it has now gone from 1, 1 to 0.5, 0.5 on both sides. Okay, so that was just kind of playing around with those. And I'm going to bring back our note. Okay, so hopefully you did that on your own, you chatted, or you watched my video and you were like, oh, okay, you kind of jotted some things down. Okay. The weirdest part about transformations this year is that the roles of the letters change. So last year we talked about equations in vertex form, and we talked about h and k being the vertex and all of that good stuff. For whatever reason, they changed the letters on you this year. So we still use K, but in a completely different context. And A sticks around, and then we have C and D instead of H and K. Okay? So hopefully you'll just get used to that from seeing it. But the real definition of K, I guess, is that coefficient that was attached to X. So I will highlight so that you guys can see that clearly. So every single one of those functions was of the form like f at k times x, which just means that that k value or that stretch or that reflection is within the function. Okay, so it's hiding right inside your parent function. Okay, so all of those are k values. And there tends to be some confusion, so I'm going to make a pretty big fuss about k values. And it'll make more sense why in a minute. So like for this j at x function, k equals 0.25. And for h at x, k equals 2. For this one, k is -1. And then remember, if you're multiplying, because it's a multiplier, here k is just 1. So in your parent functions, that k value is 1. Okay, but those are the k values that we're working with. All right. And then you can fill in whatever you'd like in that what did you notice about the functions that you graphed. Describe that in your own words, but think about some of the things that I just said, right? So a negative k value causes a reflection over the y-axis. That's one that I think we probably want to make sure we have in there. Make it smaller and I'll actually type it. So negative k value over the y-axis. You might talk about a k value greater than 1 makes the graph compress, for lack of a better word. The root function got wider, the reciprocal got closer to the axes, okay, and then a k value less than 1 makes the graph stretch in a horizontal direction, okay? So everything that's happening is in a horizontal direction. I'll flip back to Desmos for a second to point at that and show you what I mean. Probably we can see it better with the root functions. Okay, So when I stretch horizontally, if I grabbed onto the red and I pulled it out towards infinity on the right there, I would get the purple graph, right? I would stretch it out that way. But if I squished it in, so if I took this end and pressed it that way, I would get something more like the green because I would be compressing it. Okay, so it's just in the opposite direction to what we're used to. We're used to stretching and compressing in a vertical direction. Okay, so I have some fill in the blanks down here that you can probably fill in now because I just wrote them above. But in theory, if I were in class, we would talk about when k is negative, the graph reflects over the y-axis. When the absolute value of k or the magnitude of k is greater than 1, so even if it's like -3, all that the negative does is reflect it, and then the 3 does the work. We're going to say the graph is horizontally, sorry for the bad writing, compressed. Here's where it gets tricky. We still say by a factor of, like when we stretched parabolas and things, but it's 1 over k. So if my k value is 2, I would say it was horizontally compressed by a factor of 1/2. Okay? And then when the magnitude of k is in between 0 and 1, so it's a fraction, or like our 0.25, then the graph is horizontally, now I'm just writing on the bottom edge of the tablet too, horizontally stretched by a factor of 1 over k. Okay, so again, you flip it. So my 1/4 would be that it was stretched by a factor of 4. Okay, so that k value that's inside the function is different from the a value we saw with parabolas that was outside the function, because the k value is creating a division. So you're multiplying by the opposite, 1 over k, or you're dividing by k when you're trying to apply those stretches. So I'll show you how that works on the next slide. Okay, so again, most important thing to remember, k is the value that's in your equation attached to x, but your transformed point, so if I'm going to apply a horizontal stretch or compression or anything like that, is x divided by k. Okay, so that k value doesn't affect your y coordinate at all, but we are now working on the x's. Okay, so when we worked with parabolas, we didn't really apply a stretch to x ever. All right, so I've given you a table of values here. Okay, so I have x values, and then I have the corresponding point on the square root of x. Okay, so when x is 0, the root of 0 is 0. So this is the table that we had from whenever that was, last Friday, whenever we talked about parent functions. So this is just my regular table of values. What I'm going to do to produce points for this graph is take all of my x coordinates and divide them by 3. Okay, so this 3 tells me k equals 3. So the only thing that's going to change are my x coordinates, and what I need to do is take every x and divide it by 3, and then just keep the y that I had. Okay, so when I go to write new points, and you're going to have to keep doing this all the time, so you might as well start to embrace this idea. I'm going to take 0 and divide it by 3, so it's still 0. Okay, my y's are still 1, 2, and 3. 3 is a funny number, right? If it doesn't divide evenly, you've got to leave it as a fraction. So if I take 1 and divide it by 3, I just get 1/3. If I take 4, divide by 3, I get 4 over 3, or 1 1/3, that's fine too. And then 9 divided by 3 is 3. So those are my new points, and all that I did was divide by k. Okay, so divide x by k, and that gives you your new set of points. Okay, so it's just the opposite of the last year we would have multiplied y by the a value. We're going to divide x by k to do a horizontal stretch or compression. Okay, so the last mission here is to actually do this a few times. So what we want to do is graph our parent function and then graph our transformed function. Okay, so here, take that second to identify your parent function, right? So my parent, that hasn't happened in a while. There we go. All right, parent function is y equals x squared. Okay, so we know that graph. So my points on my ordinary function are going to be -2, 4, -1, 1, 0, 0, 1, 1, and 2 and 4. Okay, so that's what you plot first. And you don't always have to show the parent function, but I think for us, while we familiarize ourselves with all these new graphs, it's not a bad idea. So I'm going to do my best on my little crummy tablet here. You're going to do better with a pencil and paper. Okay, and then when I want my new points, I'm just going to take all of my x's and divide them by 3. Okay, so I'm going to have x over 3 and y. So your y's stay the same. It's a 1, I promise, and then 2/3 and 4. Okay, so do your best when you're trying to find those points. I will use a different color. This will be a nice little colorful graph by the time we're done. So this is going to be my graph of y equals 3x squared. So I'm looking at -2/3 and 4, right? So -2/3 is not even 1. So this point has been pulled all the way into there. And same on the other side. And then this guy is a little closer, and 0, 0 remain the same. And then you do better than I do at drawing yourself a very narrow little parabola. Another way to look at a quadratic, and this really only works for your polynomial function, so quadratic and cubic. You could also square this, but it's not 3x squared. This graph is not the graph of y equals 3x squared, but it would be the same as the graph of y equals 9x squared. Okay, so those would be the same graph because the exponent is being applied to the 3 as well. It also talks to you about invariant points. That's because your textbook asks about them all of the time. My thing that did not move here was my vertex. So that stayed the same. Okay, so the vertex stayed the same when I stretched, which makes sense. All right, next color. So here again, always think, what is my parent function? It's just root x, right? So then we know some points, and again, refer back to your chart from the other day if you need to. But we had 0, 0. It's also right above 1, 1, 4, 2, 9, 3. Okay, we can get that on there. So 1, 4, and 2, 9, and 3. Voila. So there's root x. Now, I do want you guys to take a second and like really focus when you try to work with the k value that is an exponent. Okay, so I'm looking here and I'm like, okay, k equals -1/2. So I want to do x divided by -1/2. That is the same as multiplying x by -2. Okay, so to get these new points, I'm going to go -2x and y. So 0, 0 is going to stay that invariant point. It's not going anywhere. But I should see a reflection and a stretch, right? Those are the two things that I'm expecting when I see a fraction of 1/2 that is negative. Okay, so now I would have -2 and 1, -8 and 2, and one that's definitely off the graph at -18 and 3, which is okay, as long as you have a few points. Okay, so we've reflected it and we've applied a stretch to it all in one step. Because it is now, again, for lack of a better way to describe it, a little narrower, a little closer to the x-axis than root x was. Okay, and I'll just continue with the highlighter on the invariant points. So the point at the vertex didn't change, like the starting point of your graph remains the same. All right, and then here, this looks ugly, but what we have is a parent function of y equals 1 over x, and that was the one with the funky table because we have asymptotes. And so we had like x and y, and we used -2 and -1/2, -1, -1, -1/2, and -2. And we had that like asymptote at 0, 1/2, 2, 1, 1, -2, -1/2 to get those 6 points. So I have 3 on each side, okay? Things are getting crowded in here now because of an invariant point between all of the parent functions is that 1, 1. But it's okay. I have that and that. 2 and that 1/2, -2 and -1/2, and then 1/2 and 2, -1/2 and -2. And you have your 2 sides with your asymptotes. I hope you did better than I did there. Okay, so there's my parent function. And now we're looking, and you want to, again, identify your k value and follow appropriate steps here. So k is going to equal 1/4, but then x divided by 1/4 is the same as multiplying by 4. Okay, so my new points are going to be 4x and y. Oh, not y. How about if I use the number? So -8 and -1/2, -4 and -1, and then -2 and -2. Okay, so your y's are not changing, only your x's are, and you're just multiplying by 4. Oh, that should be positive. Why did I make those ones negative? +2, +1/2. I think the struggle of trying to erase that would have been bad there. Okay, so those would be your new points. So I'll make kind of like a tealish graph here. -8 and -1/2. There, -4 and -1. So this is kind of nice because it's pulled itself away a little bit. And then -2 and -2. Okay, and then on the other side, same thing. 2 and 2. It's over here that's a mess, right? 4 and 1. 8.5. Okay, so you're still approaching those same asymptotes. The other thing that we don't have with this graph is an invariant point or something that doesn't change. So all the points changed on this one. Y's didn't, X's did, but we don't have anywhere where they like intersect at a point that we previously had, okay? Similar to the quadratic, when you're dealing with a reciprocal function, like I don't really love the idea that I have a 1/4 in the bottom there. And I also don't love that I'm going to have to divide. So my preference probably would be to apply a vertical stretch here, because if I have 1 divided by 1/4 x, that would be the same as having 4 over x. Okay, so it would be like 1 times 4 over x. And then you can vertically stretch your graph, which we'll talk about more tomorrow. But this is an option, so these are equivalent statements as well. Okay, so sometimes you can get out of having to divide just by going through and sort of adjusting your expression. With the root, you're stuck with it, but with everything else, you can kind of manipulate it a little bit to avoid having to divide. Okay, so what you're going to do today is practice. So any question that asks you to graph, please make sure that you actually get out some graph paper and do it. Make the tables, show your transformations. We're going to build on this tomorrow, and you're going to have to make a table every single time, so you may as well start today. Okay, so set up your table with your key points from your parent function. Make sure you pick the correct parent function, and then apply your k value to all of your x's. Just be careful with fractions and you will be fine. Okay, good luck.